Hello friends, the effect of seepage pressure on the effective pressure of the soil mass is very important from both gate examination as well as from engineering services examination. So today we would like to see how seepage pressure is going to affect the effective pressure distribution or effective pressure at a particular point of the given soil mass. You have seen in the previous video that effective pressure is greatly influenced because of capillary water. It is greatly influenced because of the pore water pressure variation, groundwater table variation. That is, so here, if the seepage is going to be in upward direction or in downward direction, how the effective pressure will change. That's of paramount important, particularly in earthen dam. Let's say we take an earthen dam. So today, the effective pressure effect due to seepage. So I take a earthen dam, let's say the earthen dam, and let's say here the water which is going seeping inside, and here the water is oozing out. So the groundwater table is somewhere here. If I go to any layer, say I go to A, which is at a particular distance, let's say this Z distance. Now the water is seeping and going in the upward direction. So the seepage pressure is acting over this length. Naturally, if you want to see, if you put a standpipe over here, at A, the water is going to shoot up, say up to this point. This is the original. It is the height of water here, HW. Sir, you can very well say that the groundwater is oozing out from here, and definitely due to seepage, the difference HS due to seepage. So if I want to find out the effective pressure at A, and if I know the saturated unit weight of the soil mass in kilonewton per cubic meter, then the effective stress or effective pressure at this level will be equal to gamma saturated, the unit weight, into Z. This is acting in the downward direction, the total weight. Now the water is oozing out from here, groundwater is coming out. So here the pore water pressure, U, that is going to act in the upward direction, will be equal to gamma W, that is the unit weight of water, multiplied by Z. But there is going to be seepage. Because of this head, there is going to be a net head other than the groundwater HS, so minus seepage pressure. Because it is acting in the upward direction, so there will be negative sign. If the seepage pressure is in the downward direction, the sign will be positive. Because the seepage pressure is acting in the upward direction, therefore the sign will be negative. And for sand boiling, or what we call it quicksand condition, when the seepage pressure is acting in the upward direction, the effective pressure at A becomes 0. That means it is the critical condition. So here the hydraulic gradient is the critical condition. So for critical condition, the effective pressure is going to be 0. So if it is going to be 0, so what will happen? Then you know that gamma sat minus gamma W, that means gamma saturated unit weight minus unit weight of water into Z minus PS equal to 0. This implies that PS equal to the seepage pressure is going to be equal to gamma prime into Z. So what is seepage pressure? The seepage pressure, PS, is called seepage. Pressure due to seepage. So the seepage pressure is given by the hydraulic gradient, that is the multiplied by the length over which it is acting. So here the length is Z. So critical, this hydraulic gradient into Z into gamma W. This is the, and for critical condition, I becomes I critical. Or we can say, or the seepage pressure is, what is this net head that is causing the seepage. So the net head multiplied by unit weight of water. And you know that the this can be written as this net head divided by Z into gamma W. So this net head divided by Z is called the hydraulic gradient. Therefore, I can write seepage pressure equal to Iz gamma W. So here the seepage pressure, it is going to be 0. So this is the critical condition, and for critical condition I equal to I critical. So for the critical condition, therefore I can say that PS equal to I critical into Z into gamma W. So PS equal to I critical, because the effective pressure at critical condition is going to be 0, and therefore it is the critical hydraulic gradient into Z gamma W equal to gamma prime into z. So z, the length over which the seepage is taking place is getting cancelled. Therefore, the critical hydraulic gradient is going to be gamma prime divided by gamma W, unit weight of water. Now, the submerged unit weight is given by, in terms of G, specific gravity, G minus 1 into gamma W divided by 1 plus E into this gamma W. So this gamma W and gamma W will get cancelled. Therefore, we can say that the critical hydraulic gradient must be equal to G minus 1 divided by 1 plus E. Right? So this becomes the critical hydraulic gradient. Now, for safety of the structure, this the actual value of I for factor of safety or for safety of the structure, we can say for safety, the factor of safety F must be greater than 1, or the value of actual hydraulic gradient must be less than I critical. So the factor of safety is given by I critical divided by the hydraulic gradient actual. And if there is going to be less than this, the factor of safety is going to be 1. So for safety, we can say that the actual hydraulic gradient must be less than the critical hydraulic gradient, which is given by G minus 1 divided by 1 plus E. So seepage is quite important for determination of the effective pressure, and if it is acting in the downward direction, then the seepage pressure will become positive. If it is acting in the upward direction, it is going to be negative. So the direction is very, very important that we should always look into. So we can take a problem and try to solve it. Let's say you have a clay stratum. This is the depth Z, 0.0 meter. There is 12 meter. There is clay, followed by sand, underlain by sand. So this is going to be sand. Now, I am going to dig a trench here. So a trench is being dug over here. So this is the trench I am going to dig. So this is the trench. Let's say this trench is as deep as 8 meter. And the moment I come to this 8 meter, the water is going to ooze out into the trench. So in the trench, the water, the moment you reach up to 8 meter, the water is from bottom is finding it is ingressing into the trench. So What is the seepage pressure that's causing this kind of situation? So here, if I'm putting a standpipe here, the what should be the head that will rise into this standpipe? So I'm interested in, let's say, the head in the standpipe. If I put at this 12-meter is HW. So what is this HW? Is going to be from downward, there is going to be seepage pressure. What is that head that's causing this failure at when I am going to come at this particular position? Now, at 12-meter, the total pressure you can find it out. Like say for clay, the gamma saturated is 20 kilonewton per cubic meter, and unit weight of water is 10 kilonewton per cubic meter. Then the effective pressure at 12-meter, due to clay, it is the total pressure can be calculated. It is 20 gamma saturated. And what is this length? Remaining length is going to be 4 meter, isn't it? So if it is 4 meter, the total pressure, because I have already dug a trench, so this is going to be Z, through which the water is seeping. So this becomes the total pressure minus. Now, the pressure which is acting in the upward direction is going to be unit weight of water into height of water in the upward direction. And this is in the downward direction. So when I am going to dig a trench, the water is oozing out in this. So the downward pressure I have calculated, and due to pour water, I have calculated. I do not know what is the head of water that is causing. So this can be easily found out, because finally the effective pressure is going to be 0. Then only the water will ooze out into the trench. It will ingress into the trench. So if it is going to be 0, I want to find out this one. Therefore, I can say that HW from this is going to be 20 into 4 divided by gamma W, that is 10. So this goes out, this becomes 8 meter. So the head of water is 8 meter. So the application of seepage pressure when it is in the upward direction must take the negative sign, but if the seepage is going to be in the downward direction, the water is seeping in the downward direction, then it should be taken as positive. So friends, we will take up this thing in our preparation for engineering services examination. Lot of problems we will be taking, which has been already asked in the examination, engineering services examination and gate examination. Both we will be covering up. Now, another important topic is permeability. of soils. So you know which is the most permeable soil? The coarse grained soils are more permeable in nature, and the least permeable is clay. So gravelly soil, sandy soil, and silty soil, and the least permeable is the clay soil. Highly permeable is gravelly soil. So the permeability of soil is very, very important, and it depends upon the uh, the permeability, that is the water that is going to pass through the soil mass, will depend upon the permeability, and also it depends upon Reynolds number. So Reynolds number gives you whether the flow is the velocity is laminar or it is um, not laminar. So Reynolds number will depend upon how will you find it out. If it is less than critical velocity, then Reynolds number for laminar flow, this for laminar flow condition in the soil mass. So the Reynolds number must be less than equal to 2000. And you know what is the Reynolds number. As I told you, for flow to be laminar, the critical velocity, the velocity of percolating fluid or water, here it is water, should be less than critical velocity of percolating water. So let's say the critical velocity is Vc. So Reynolds number says that Vc the critical velocity of percolating water in a tube whose diameter is d into unit weight of water, and if the viscosity of the water is eta into g, acceleration due to gravity, should be less than equal to 2000. So the conditions are well defined, that the flow should be laminar flow, and the discharge through the soil mass, the rate of discharge let's say it is Q, which is equal to total discharge divided by in a given interval of time. So the rate of discharge Q is directly proportional to, it will depend upon the hydraulic gradient. What is hydraulic gradient? You know it. That is the head loss when the water is percolating through the soil mass. Say it is the dam and water is here. The water is seeping through this. Right? So what is the head loss? Let's say the water is oozing out from here. So the head loss is going to be delta H. And the total length through which it has traversed. So the total length through which the water has traveled is called the hydraulic gradient. So rate of discharge Q is directly proportional to I, and also it is directly proportional to the cross-sectional area of the soil mass. So I is the hydraulic gradient, is the cross-sectional area of the soil. Or you can say the rate of discharge equal to the limit of proportionality K into I into A, where K is called coefficient of permeability. So for any cross-sectional area and for any given condition for a given head, the velocity Darcy gave it, known as Darcy's famous law, that the velocity of percolating fluid for laminar condition, not for turbulent condition, but for laminar condition, the velocity is directly proportional to hydraulic gradient. Or this velocity of percolating fluid is coefficient of permeability into I. So we can say Q equal to Ki becomes the velocity into cross-sectional area of the sample. So this velocity is called discharge velocity. So Q by A, or the rate of discharge divided by cross-sectional area, equal to velocity. This velocity is called discharge velocity. But the water is percolating. You know that water is composed of soil solids and void. Therefore, the water is passing through the voids. So we can say the Q equal to the water percolating through the voids is called seepage velocity, Vs, multiplied by area of the void. So if you take the three-phase diagram, you know it that the water is percolating through the interconnecting voids, and that is called the seepage velocity. This is called discharge velocity. This is called seepage velocity. And the area of the void is much less than the cross-sectional area. Therefore, this velocity is also called superficial velocity. Or we can say that V equal to Vs into AV divided by A. Or we can say we know that seepage velocity multiplied by porosity, because area of void, cross-sectional area of the void divided by total cross-sectional area will be the porosity. Therefore, the relationship between seepage velocity and the superficial or discharge velocity is given by this. Therefore, we can say that the seepage velocity, therefore, the seepage velocity equal to the discharge velocity divided by porosity. N is called the porosity. So this relationship you should always remember. Now look here that V equal to K into I. So for any soil mass, we would be interested in finding out the coefficient of permeability. So to find out the coefficient of permeability K, uh, determination of coefficient of permeability K. You have got lab test, laboratory tests, you have got field tests. So presently we will look to this field test later on we will discuss. In laboratory test, the famous test is constant head method. In constant head method, over the soil sample, which is taken in the permeameter, you are maintaining a constant head of water. So you have a overhead tank and you maintain a constant head, and the water is allowed to come out and collected in a jar. So in a graduated jar, you can collect the water and measure it in a given time. So in a given time t, time interval, what is the total discharge collected in this jar when a head is maintained, a constant head is maintained over this soil sample? So you can take a soil sample in a permeameter and allow the water to drip out, pass through the soil sample, and that discharge is Q. So you know the rate of discharge Q by T becomes the rate of discharge. So therefore, Q by T, Q equal to K, coefficient of permeability, into I, into cross-sectional area of this sample is capital A. And I is going to be equal to K into what is the head loss? If say the total head above this up to here is delta H, is the head loss, then it is going to be delta H divided by, it is passing through the length of the sample. So length of the sample is L. So hydraulic gradient is going to be delta H divided by L into the cross-sectional area. Therefore, you can easily find out the coefficient of permeability by constant head method, K equal to Q L divided by A area into delta H into T. So a simple way, Q you have already in a given interval of time T, you have collected the discharge in this measuring jar, and the length of the sample you already know in the permeameter soil sample. The cross-sectional area, if you know the internal diameter of this circular permeameter, pi by 4 d square, the diameter of the permeameter will give you the cross-sectional area of the sample. And you know what is the head loss. that you can always measure it in the laboratory. And in a given interval of time in a steady flow, when the flow becomes constant, then when the sample remains fully saturated, the constant steady condition, you can achieve it. So, you know everything on the right hand side, therefore, the coefficient of permeability by constant head method, you can find it out. But the sufficient discharge should come out in a given interval of time. So, this constant head method is suitable for coarse grained soil. In coarse grained soil sample, you will find that you get sufficient discharge. But if it is fine grained soil like clay, then discharge in a given interval of time is almost not measurable. Therefore, we go for another lab test, and that is called variable head method. This variable head method is normally used for fine grained soils. So, in a variable head method, you have the soil sample in the permeameter, and you put a stand pipe. The cross sectional area of this stand pipe, you can measure it, internal diameter. So, the cross sectional area of the soil sample is also known to you, and you allow the water of this permeameter to come out by opening the valve. The water is there in the pipe, and that height at time t equal to 0 is h1, and at time t equal to t1, this height becomes h2. Then, applying this Darcy's formula, you can find it out that the coefficient of permeability is given by 2.3. The cross-sectional area of this pipe in which the water is going to drop down into the length of the sample. So, this is the soil sample, the length of the soil sample, AL divided by the cross-sectional area of the sample into time interval into log of H1 upon H2 to the base 10. This is the famous formula using which you can find out the coefficient of permeability. On the right hand side, you know everything. You have in the laboratory, you have already recorded, and therefore the coefficient of permeability can be easily found out. So, friends, for today, I would like to sum up over here, and in the next video, we will take up few numericals on this, and I am going to take up now both GATE as well as engineering services questions, and I would like to give you the broader view of both the question paper. That was the request from all of you, and so I am going to comply. Thank you very much.